Hello everybody, and welcome. It's Obi-Wan Pez for N-Simplex Pachinko. We are going to be doing some mathy type stuff tonight, reading through papers and whatnot. I did do a very specific choice for the initial song today, Circe by Lilith Max, who came out with that one, I think a year or so ago. Specifically in response to the recent understanding of the horrifying online communities. Yep, you know which ones I'm talking about. So rather than We're the Revolution, we listen to Circe tonight. So, we'll play that again later. Hope you all are having a good evening on this Monday. And we're going to go back to talking about, yep, that's the one. Angel, Armanchuk, Bradenberger, Donderwinkel, and Kanfer, speaking about the largest common subtree of two random trees. Now again, I don't know really anything about this, and we may decide to stop somewhat through this and check out. This last one we have is linear geometry. We were talking about flats, ranks, regularity, parallelity. There we go, and several other little bits about it to try to understand what is linear geometry. So we may pop back to that. We may, in fact, go over and look at some of the other papers that have come up since I have added these in. And again, I hope you all are having a good evening, so we'll see how this goes. Okay, so 1.1, let us briefly present some concrete examples of cases where theorem 1.2. Assume that 1.1 and 1.2 hold, which were the critical and non-trivial offspring distributions. So the sum of... we need to remind ourselves what all these things mean. Mu is equal to mu of k such that k is greater than or equal to 0, and mu prime equals mu prime of k, where k is greater than or equal to 0, be two critical and non-trivial offspring distributions. Okay, so that k times mu of k and the sum of all k times mu of k and the sum of all k times mu prime of k are equal to 1. And mu of 0, mu prime of 0 have to be greater than 0. Alright, mu and mu prime have finite second moments. Sigma squared is going to be defined such that the sum of all k minus 1 squared times mu of k is less than infinity. And same for sigma prime squared. Let us denote by tau and tau prime two independent binomial trees with respective offspring distributions mu and mu prime. Formal definition of binomial trees given in section 2. So, helpful. Sorry, the other one was particularly quiet. P of number of tau equals n greater than 0, and P of, I keep wanting to think P is probability. Might be. P of number tau prime equals n is also greater than 0. Then for any such n, denote tau n and tau prime n, two independent Bienname trees with offspring distributions mu and mu prime respectively, and conditioned to have size n. We view tau n and tau prime n as compact metric spaces equipped with their graph distances. So compact metric spaces would also be something useful to know about, obviously. Okay, compact metric space satisfies the following properties. The open interval between x and d, open interval, I don't believe that's an open interval, hang on. Okay, topological space X is called compact if every open cover of X has a finite subcover. X is compact if for every collection C of open subsets of X, X is equal to the union of all S's in C. Then there is a finite subcollection F, which is proper subset of C, such that X is equal to the union of all S's in F. I did study some of this stuff with Zach, but unfortunately have not remembered every single little bit of it. So okay, some branches of mathematics, such as algebraic geometry, typically influenced by the French school Bourbaki, use the term quasi-compact for general notion. Reserve the term compact for topological spaces that are both Hausdorff and quasi-compact. Don't know what Hausdorff is offhand. T2 space or separated space, topological space where distinct points have disjoint neighborhoods. Okay. So this has to be like points that are non. Distinct points have disjoint neighborhoods. So okay, so standard real numbers are going to be Hausdorff space because you can create neighborhoods around each of those distinct points. No matter how close they are, there's always a neighborhood around them that don't include each other. Okay, so that's fine. All right, compact set, sometimes referred as compactum. Subset K of a topological space is compact if every arbitrary collection C of open subsets of X, okay, such that K is a proper subset of the union of all S's in C. Then there is a finite subcollection F subset of C such that K is a proper subset of the unions of all S's in F. Okay, so same thing as subsets are compact as well. Equivalently, K is compact as a subset of X if and only if topological space K is compact in subspace topology. Ah. Topological space X comma tau, or what we had X comma D in several of the other things. So that's not an open interval. Oi. Okay, so X comma D is going to exist such that X is the topological space and D is the subspace topology. Or inherited topology, induced topology, or trace topology. Great. Okay. Subset S of X, the subspace topology, tau, on S, the subset, is defined by tau sub S, which is defined by S intersect U, where U belongs to tau. The subset of S is open in subspace topology if and only if it is the intersection of S with some open set in X tau, or XD, how we had been doing it before. Okay. If X is a topological space, then the following are equivalent. X is compact, so every open cover of X has a finite subcover. X has a subbase such that every cover of the space by by members of the subbase has a finite subcover. X is Lindelof and countably compact. Any collection of closed subsets of X with finite intersection property has a non-empty intersection. closed subsets in X with a finite intersection property. Any finite subfamily has non-empty intersection. Any finite subfamily of the family of subsets of a given set as a non-empty intersection. Okay, so all a particular family of subsets. Every net function whose domain is a directed set on X has a convergent subnet. Every filter can be used to study topological spaces, define basic topological notions like convergence, continuity, compactness, and more. Filters, which are special families of subsets. Yeah, okay, that makes sense. Has a convergent refinement. I don't know what that necessarily is. Every net on X has a cluster point. Every filter on X has a cluster point. Every ultra filter. Maximal filter on X. In other words, that it's a collection of subsets of X that satisfies definition of a filter on X and is maximal with respect to inclusion, since there is not a strictly larger collection. Okay. Every infinite subset of X has a complete accumulation point or cluster point. Complete being slightly different. Every neighborhood of little x contains a point of capital S other than X itself. Okay, so that's a bit like the Hausdorff thing that we talked about before. Your neighborhood around any point has to have other stuff in it, not just not just the point in question. Every infinite subset on X has a complete accumulation point. Every topological space Y, the projection X by Y into Y is a closed mapping. Which maps closed sets to closed sets. Every open border linearly ordered by subset inclusion contains X. For any subset A of Euclidean space, for example, A is compact if and only if it's closed and bound. As the Euclidean space is a metric space, these conditions in the next subsection apply to all of its subsets. Of all of the equivalent conditions, it is in practice easiest to verify that a subset is closed and bounded. Example for a closed interval or closed n-ball. For metric space XD, the following are equivalent, assuming countable choice. XD is compact, following all the above definitions. XD is complete and totally bounded. Every Cauchy sequence of points in M has a limit that is also in M. We were talking about Cauchy. Thank you, canonical form. How's it going? So this is looking at the largest common subtree to two random trees. So graph theory. As far as I know. And we were looking at the proper definitions of compact metric spaces, because I figured I was going to have to know that in order to continue much beyond here. I've got the metric spaces information over on the other screen, just so that I can go through the definition and try to make sure that I've got everything. I don't, but you know, we try to do what we can here. So we were talking about complete spaces, complete metric spaces. Have every Cauchy sequence of points M in M has a limit that is also in M. So we talked about this with Zach a while back, doing real analysis. So for anybody who knows Zach, man, got too much stuff in the way here. Zach is each of the two iPi on Twitch and knows a lot more about real analysis than I do. Feel free, anybody who's out there, go follow his channel. He's got some really awesome stuff going on. And going to be working with Penn Center in... Actually, they have a podcast together. Where they talk about math education and do some awesome stuff. So usually I think they dual stream. Could just be on Penn's channel though. I don't remember how they actually have it set up. Doesn't matter. Complete again. So the metric space will be, or the metric space has to be complete. So you have some sort of sequence which is going to lead up with a bunch of points, and then based on those individual points, there is also a limit to that point, or to the sequence of points, which is also going to be in the metric space itself. Totally bounded. Generalizes the compactness for circumstances in which a set is not necessarily closed. Totally bounded set can be covered by finitely many subsets of every fixed size. Okay. Uniform spaces. Set with additional structures used to define uniform properties like completeness, uniform continuity, and uniform convergence. Generalizes metric spaces and topological groups. Okay, XD is sequentially compact. That is, every sequence in X has a convergent subsequence whose limit is in X as well. If the sequence is in X, then the convergent subsequence must... Oh, the limit must also be in X. Boy. XD is limit point compact, also called weakly countably compact. Every infinite subset of X has at least one limit point in X. Okay. In topological space, point little x can be approximated by points of big S, the set in question, in the sense that every neighborhood of little x contains a point in S other than x itself. Right, so x is not an isolated point. It's going to include other stuff that's in the set in question. That's fair. Bestow this. We're trying to read about compact metric spaces at the moment. However, overall, we're reading about common subtrees. So if two random trees are built, then they wanted to isolate the two largest subtrees of those two randomly generated trees. Yes, this is a research paper, and let me throw the arXiv link into chat. Oh, curses. I have to move stuff. So generally speaking, on Mondays we do some literature review, so we go through all of the we go through some relevant papers that I have any hope of understanding whatsoever, which generally speaking is small, and many times we find that I have no hope of understanding what's actually in the paper. But that's fine. We try to learn something. And if anybody in chat has any particular experience with stuff, then it also helps because you all can bring some of your experience to it as well. Yeah. Yep. That's usually how it rolls. Have you taken real analysis? And did you enjoy it? Very different question. Okay, so if X is empty or XD is the image of a continuous function from the Cantor set, so here the Cantor set being the one that takes a set, we can divide it into thirds, and the two disjoint subsets after removing the middle one can be broken into three themselves, and then we remove the middle one from each of them, etc., etc., etc. So we want to know if like single individual points are able to be like single individual points will be part of the set, but then right, self-similar set of points lying in a single line segment has a number of unintuitive properties. Recently bought 2 books by Cummings and enjoy the one about real analysis. Haven't touched the second one, being proofs. Okay. I imagine that this is a bit higher level than the proofs book that I took in sophomore year. This is A Transition to Advanced Mathematics by Chartrand, Polemeni, and Zhang. Which goes through, like, you know, basic examples of contradiction and direct proof and all this good stuff. It was good for what it did, but I enjoyed that one far less than my senior level proofs book, which amusingly, because I was in math education, not pure math, was actually easier to understand. Covered basically all the same examples. And then it ended up being the source material that we, as math education majors, used to teach each other the material. So the idea was like, we already know this material reasonably well, so now we're going to go back and we're going to actually learn how to teach it to each other. And so we did, basically, he went down the register and just was like, okay, you're doing week 1, week 2, week 3, week 4, etc. Prep that particular lesson. And like every day that we meet, you're going to do the next section, etc., etc. And when we got to, there were only like 6 of us, so I mean, we each took 3 lessons, I think, over the course of the full semester. And then when you're done, everybody gives like critique and tries to analyze, like, you know, how did you do this? How did you plan your particular material? How do you think it went? There was a bunch of really good stuff. Okay. Every decreasing nested sequence of non-empty closed subsets S1, S2, S3 being all supersets of the following one in XD has a non-empty intersection. Every decreasing nested sequence of non-empty closed subsets has a non-empty intersection. So okay. Every increasing nested sequence of proper open subsets, S1 being a proper subset of S2, proper subset of S3, etc. in XD, fails to cover X itself. Fails to cover the entire metric space. Because all of the S's are open. Okay, it's the open and closedness that threw me, I think, there. So open subsets will fail to cover X because all of their elements need to be within X. And there's never an edge of the open subsets that can actually hit every single X value, or every single element of X in the space. I think that makes sense. You have that one as well? Oh, man. Chapter 0. I'm not sure what you're going for on that one, sorry. The one that we did as math education majors was doing mathematics. Is that chapter 0? I mean, I don't think it's just called... It has a chapter 0 called Communicating Mathematics. Yeah, my spouse used this book like a semester or two before I did. A Transition to Advanced Mathematics. Ah, okay. Let's see. Whereas every decreasing nested sequence of non-empty closed subsets will have a non-empty intersection, because if it's a closed subset, then it has to include something. Can't have a non-empty intersection if it's also a closed subset. Compact metric space XD also satisfies the following properties: Lebesgue's number lemma. For every open cover of X, there exists a number delta greater than 0, such that every subset X of diameter less than delta is contained in some member of the cover. Yep, all right, makes sense. This is basically just a delta epsilon proof, but now we're talking about neighborhoods. XD is second countable separable and Lindelof. These three conditions are equivalent for metric spaces. Converse is not true. A countable discrete space satisfies these three conditions but is not compact. X is closed and bounded as a subset of any metric space whose restricted metric is D. Okay. Converse may fail for non-Euclidean space, e.g. the real line is equipped with the discrete metric. The real line equipped with the discrete metric is closed and bounded but not compact, as the collection of all singletons of the space is an open cover which admits no finite subcover. It's complete but not totally bounded. Okay. I may slightly understand it enough, however. Hey, Poison Mouse. Yeah, the one that I showed was A Transition to Advanced Mathematics, which was the proofs book that my spouse and I used in our sophomore year. Or for sophomore level proof. But that's not actually what we're doing. I was looking up the definition for compact metric spaces because that's here. There we go. Compact metric spaces. Okay, for any compact metric space E, ED, and lambda greater than 0, we write lambda E equals E lambda D for that metric space, obtained by rescaling the distances on E by lambda. It's now well known that this. It is well known, yes. Not by me, but by many other people. All right, within the metric, within the definition, topological space. Oh, shoot. Lost the point of that again. Subspace topology. There we go. Within the subspace topology D, as n goes to infinity, 1 over root n times tau n, comma, 1 over root n times tau prime n is going to approach 1 over sigma times fancy t, comma 2 over sigma prime times fancy t prime. With respect to the Goromov-Hausdorff topology, where fancy t and fancy t prime are two independent Brownian continuum random trees. Yes, it's a fancy t. So if you turn, if you do a Word document and type T, capital T, and then change it to like script or cursive, something like that, then that's what it's going to look like. But yeah, they were going for, oh, let's take tau and then like change it into something. It's kind of gross. More precisely, if E equals E sub S, where S is between 0 and 1, is a standard Brownian excursion. No idea what that is. T and T prime have the same law as the quotient metric space of 0 to 1, induced by pseudo-distance d sub E, defined as follows. For all S1, S2 between 0 and 1, inclusive, such that S1 is less than S2, d sub E of S1, S2 is E sub S1 plus E sub S2 minus 2 times the minimum of E with regards to S1, S2. Finally, introduce limit quantity. For any two compact metric spaces E equals ED and E prime equals E prime D prime, set phi of EE prime to the supremum of that. When E and E prime are compact real trees, then phi of EE prime corresponds to the maximum total length of a common Y-shaped subtree of E and E prime. Okay. For details on compact real trees, the Brownian continuum random tree, and Gromov-Hausdorff topology, we direct the reader to 27, also 5.1 for brief summary. Let tau star and tau star prime be two independent rooted trees whose laws are characterized by the following. For all integers k greater than or equal to 0, the root of t star has k children with probability k plus 1 mu of k plus 1. And root of t prime star has k children with probability k plus 1 mu prime k plus 1, mu prime of k plus 1. Conditionally, given the offspring size of the root of tau prime, respective in tau prime star, tau star prime, subtrees of tau star above these children are independent Bianami trees with offspring distribution mu. I guess similarly to using the primes, it can be replaced without any special consideration. We refer to random rooted trees tau star and tau star prime as root biased Bianami trees with offspring distributions mu and mu prime respectively. Oh, yeah, respectively replace all regular stuff with prime stuff. It's all good. For rooted trees T, T prime, and T double prime, we say that T double prime is common rooted subtree of T and T prime if there are graph isomorphisms from T double prime to both T and T prime that map the root to the root. Write LCS dot T T prime for the maximum size of a common rooted subtree of T and T prime. We're now ready to state our main result in full form. Okay, we have figure 1 below, which is giving highlighted in red the two largest common subtrees between these two randomly generated other trees. Okay. If there exists kappa greater than 0 such that the sum of all k to the 2 plus kappa of mu of k summed as k is greater than or equal to 0 is all less than infinity, then the following convergence in distribution R holds jointly with 1.3 from above. 1 over root n times the LCS of tau n prime is going to, through the subspace topology D as n goes to infinity, as n gets larger and larger, is going to become C sub mu mu prime times, that's a set. Boy. That looks like multiplication, but it's a set, so you can't really do that. Phi of 2 over sigma times t, 2 over sigma prime times t prime. Proofs, in fact, give under the assumptions of theorem 1, 2 that for any c greater than 0, okay, it is a constant apparently. Okay. 1 over root n times LCS of tau n tau prime sub floor c times n. It's going to approach c sub mu mu prime phi of that stuff. But to ease notation, we'll not prove this in a more general form. Okay. Cool. Let's present concrete examples of cases where theorem 1, 2 applies. The family of size-conditioned critical Bienname trees with finite variance offspring distributions contains several usual combinatorial families of random trees. In fact, one does not even need to look past the offspring distributions with finite exponential moments to find many well-studied models. Here are a few examples. If we set mu of d equal to 1 minus mu of 0 equals 1 over d for some d greater than or equal to 2, then tau n is distributed as a uniform d-array tree on n vertices, assuming that n equals md plus 1 for some integer m greater than or equal to 0. Okay. In this case, n is odd, then. May not matter. If we set mu of k equal to 2 to the negative k plus 1, for all k greater than or equal to 0, then tau n is distributed as a uniform rooted plane tree on n vertices. If we set mu of k equal to e to the negative 1 over k factorial for all k greater than or equal to 0, then after randomly labeling the vertices, Tn is distributed as a uniform labeled tree on n vertices. Theorem 1, 2 applies to any pair of trees from the above list, again ignoring labels, and plain order when looking for common subtrees. One may wonder if the condition that one of the two offspring distributions has to have finite 2 plus kth moment is necessary, or just a consequence of techniques. The following result shows that theorem 1, 2 is false if we allow k equals 0, implying that our theorem is tight in this generality. For any gamma less For any gamma less than 1/2, there exists a critical and non-trivial offspring distribution mu, satisfying that the sum of k squared times mu of k is less than infinity, such that for mu prime equals mu with high probability LCS is greater than or equal to root n log n, natural log of n, raised to the gamma as n approaches infinity. We proved this theorem in section A. No, thank you. 45 pages. Oh, man. Okay, so yeah, we're not going to understand this, so. So let's at least see if there's anything here that we can get useful. For all v in P subtree of T dot rooted at V that branches off from P has size bounded above by this thing, some fixed V greater than 0, but some of the sizes nevertheless bigger than h to the epsilon. Oh, that's a nu. That is not a V, that's a nu. Epsilon minus nu. ht of tau. Heavy-tailed. Okay. So heavy-tail random walks are these ht of tau and ht of tau prime. So by taking these heavy-tailed distributions and then anding them using a logical operator. Come on. There's some vertex V in P such that the subtree rooted at V, which branches off from P, has size bigger than h to the epsilon minus nu of our heavy-tail distributions anded together with +1. Okay, can use known tail bounds for sizes of B and MA trees, along with big jumps principle for random walks, to show that 1 has exponentially small probability. By the construction of P, if 2 occurs, then both subtrees stemming from V in T dot are larger than the given number. By independence of disjoint subtrees and B&ME trees, we then approximately obtain 2 independent copies of the bad event, B sub epsilon minus nu, allowing a divide and conquer strategy using previous iteration of bootstrapping. This allows us to improve upper bound on 1.5. Recursively applying the argument then gives an arbitrary good polynomial bound. One key consequence of having good bounds for 1.5 is that P of LCS dot of tau prime is greater than h, which must be less than or approximately equal to h1 over h squared. Convert our understanding of common rooted subtrees of unconditioned trees from section 3 to unrooted common subtrees of conditioned trees. Specifically, we show that LCS of tau n prime is well approximated by the constant multiple of LCS sub big N, where LCS sub big N denotes the total length of the largest common subtree with only n greater than or equal to 3 leaves. says that typically a largest common subtree consists of a large skeleton with at most n leaves and LCS sub n of tau n prime edges, combined with small trees hanging off the skeleton that collectively obey a large law of large numbers behavior. Indeed, this is where the factor c sub mu prime comes from. For a given vertex on the skeleton, approximately the corresponding pendant trees in tau and tau prime are independent, and the expected size of their largest common rooted subtrees is c sub mu prime. Bounding 1.6 amounts to showing that the largest common subtree contains a bounded number of macroscopic mass splits, and to making the approximate law of large numbers precise. Finally, we use that our bounds decay quickly enough for our conclusions to also hold for the conditioned trees tau n prime. Okay. Ads are going to start here in about 2 minutes, so just letting everybody know. Gonna get up. I barely started on my coffee, so probably won't get a drink. Might get a snack. Conclude with a number of potential directions for future work. Okay, helpful. Although this work is the first on the topic of largest common subtrees of two bionime trees, largest common subgraph problems have been growing subject of interest in recent years. Here we review some work that has been done and highlight some various motivations. Earliest work on largest common subgraph problems in mathematical context comes from a study of maximum agreement subtrees for uniform labeled there we go. Uniform random leaf labeled binary trees. Let T and T prime be two binary trees with n leaves labeled by 1 through n for subset A belonging to being a subset of that set. The tree T restricted to A is the tree obtained by contracting all edges incident to vertices of degree 2 within minimally connected subgraph of T that contains all leaves labeled by A. The tree T prime restricted to A is defined analogously. Call a leaf-labeled binary tree T star an agreement subtree of T and T prime of size M. If there is a set A within 1 to n of size M such that T and T prime restricted to A both equal T prime. T star, man. Ugh. Maximum agreement subtree is of maximum size. Upcoming paper, consider the largest type of common subtree in two independent random recursive trees. Find the polynomial lower bound n to the alpha for some alpha greater than or equal to 0.8, and an upper bound of 1 minus epsilon times n for some epsilon. In particular, largest common subtree of two random recursive trees, size n and asymptotically much larger than n to the 1/2, which is the order of the largest common subtree of two bionime trees of size n under our assumptions. They conjecture that the asymptotic size is in fact n to the 1 minus O of 1. Lowercase o I don't have anywhere. But, all right, we'll be back in 3 minutes. Thank you so much, everybody, for coming. And yeah, be right back. Get up and stretch and do all that stuff. Welcome back, everybody. All right. Despite being a relatively recent topic of study in mathematics, the computational complexity of identifying large common subtrees has been discussed for some time within the theoretical computer science community. Yes. Focus has not been limited to trees. See 18 for algorithms concerning large common subgraphs in more general settings. Another model which has largest common subgraph problem has received attention is Erdős-Rényi random graphs, G of NP in the dense regime. In contrast to the results for Bien-Aimé, the size of largest common induced subgraphs between independent Erdős-Rényi random graphs has been shown to exhibit strong concentration. For two independent G of n 1/2 graphs, 10 shows that it concentrates on two values, both with leading order term 4 times the log base 2 of n. This 2-point concentration phenomenon has been extended to GNP and GNQ for P not equaling Q, not depending on n. Largest common induced subgraph for problem G of NP is related to the graph isomorphism problem, classic topic in the computer science literature. Topic beyond simple graphs, largest common hypergraph between two uniform D hypergraphs is studied in 28. Final note, we highlight the work on longest common subsequences for random words, which predates literature on the common subgraphs by some time. With its origins in computational biology, the problem of studying longest common subsequence between two random strings of length n over finite alphabet has received a large amount of attention over the years. Longest common subsequence problem for independent random permutations has also been extensively discussed. Really? 6 pages of actual thing? And then, oh, okay. Preliminaries. There we go. Right, that was just the introduction. Oh, man. Shape characteristics. Okay. Anyway, I already said we weren't gonna understand any of this, so it's all good. I am effectively correct. It's Desired theorem 1.2 could be understood by saying that for large critical Bien-Aimé trees, the size of a largest unrooted common subtree is roughly proportional to the size of the largest common subtree with 3 leaves. So the intermediate step we show in this section that the size of the largest common subtree can be approximated by a multiple of total length, that is, number of edges, of the largest common subtree with boundedly many leaves. Hence, for two trees, TT prime with integer n greater than or equal to 3, let's denote LCS n of TT prime, the maximum total length of an unrooted common subtree of T and T prime with at most n leaves. Goal of this section is prove the preliminary result for theorem 1.2. Bad cases, yes. Okay, so something like this, right, is the triangles are just representing any other tree that's attached to this particular thing. They highlighted that up above a few pages ago. I didn't comment it on back then, but nonetheless. Here, our common subtree starts from this V-shaped bit here. And it doesn't even matter necessarily how long it is either, but right. Collapsed R depicted on the right. Right. Okay. So it's trimming out all these blue ones and saying, like, this is irrelevant stuff if we're talking about the space of common subtrees. So the red triangles are the vertices, which, like, make the sort of decision points, the places where it branches in the appropriate directions. I can understand that, at least. So all the blue ones are getting trimmed out. That's trees in T off the vertices. In R, R remove, collapse R. Okay. T unrooted common subtree with maximum size by phi. T mapped to tau, and phi prime, T mapped to tau prime, corresponding embeddings. Define R0 as the endpoints of those edges of T whose removal disconnects T into two components with sizes bigger than n to the 1/2 minus 2 alpha. If R0 is non-empty, then it is a subtree of T. We set R equal to R0. If R0 is empty, then we set R equal to singleton R, where R is a centroid of T. Vertex whose removal splits the tree into components containing at most half the vertices of T. Note that as a subtree of T, R is a common subtree of tau, tau prime. See figure 5. It was this one. Yeah, okay. Bad event, sausage or twig. Partition the path from U to V. U to V. In tau, and the path from U prime to V prime in tau prime of the same length into 7 parts. Define partition that we'll use to prove the lemma. Bad event 2, skewer. Ian Stuckey. Hey everybody. This is Ian Stuckey. They are another friend of the channel, math streamer, and all-around awesome person. You should go follow them. Big programmer error message energy, yeah. No, you're an awesome person. I'm just going to steal everybody else's emotes. It's alright. I need to get back over to Steve's channel. because they have a really good she's got a really good emote for no you. It's she's looking out kind of accusingly, and the sign just says no you. Although apparently this one's pretty good, so. Selena? Completely irrelevant, but nonetheless. For anyone who did not see this yet, that is the archive paper for this particular thing that we're working on. I'm well beyond, it's well beyond my understanding, honestly, but it is still pretty good overall. Seems like it's not just making stuff up, so I just can't quite understand it. We don't need more proofs. Paths from U to V in tau and U prime to V prime in tau prime with matching hanging subtrees. Okay. Branching property, given m is greater than or equal to 1, the right-hand side is bounded by 2c n to the negative m for sufficiently large d, and therefore, using the one-to-many principles, lemma 4-7, that says 2-7. Let tau be a binomial tree with offspring distribution mu. Let m be the set of integers such that p of number tau equals n greater than 0. If this is true here, less than infinity, for some gamma greater than or equal to 2, then the limit as a goes to infinity as n goes to infinity for n belonging to m of p, of p having a using a maximum of k sub nu of tau, as nu is a member of tau greater than or equal to this stuff, it's going to be equal to 0. So that means that they have no connection. They have no greatest subtrees, I think was the idea there. When d is greater than or equal to 10, this p is less than or equal to the sum of p's under those conditions. Boy. Bad event 3 flowers. That was basically the sub trees that were being trimmed were basically all around a cycle or something like that. I think we're passing too much stuff. Yeah, all right. Study of common subtrees. of random trees is still in its infancy and a wealth of natural questions remain. Here's a few. We believe our methods can be used to prove that under the assumptions of Theorem 1-2, the following is true, jointly with 1-3, that this may even hold with both mu and mu prime have only a finite second moment. What is the size of a largest common subtree of if the offspring distributions have power law tails and no second moment? In this case, the largest common y-shaped subtree of tau n and tau n prime has a length of order n to the 1 minus 1 over alpha, which is much less than root n. However, both subtrees contain a star with size of order n to the 1 over alpha prime, which is much greater than root n. Suggests that largest common subtree in tau n and tau n prime is very wide in contrast to the setting of Theorem 1.2, which gives a very tall largest common subtree. Conjectured that the largest common subtree of tau n and tau n prime is of the same order as the minimum of the maximum degrees in the two trees, that n to the negative 1 over alpha prime times LCS of tau n prime has a random limit under rescaling. Okay, what happens if we allow small distortions between two subtrees, allowing them to not be exactly isomorphic? What happens if we allow replacing in an edge by a path of length 2 at most k times? For fixed k, this should not change the conclusion of Theorem 1.2, but what if k is much greater than 1? In particular, what is the threshold kn star for the largest common perturbed subtree to be much larger than root n? Appendix for proofs. And then references. All right. Cool. All right. Sorry, guys. It gets very dense, and if you don't know the actual material, which I don't, it just gets really hard. All right, this linear geometry paper I want to get back to at some point and start looking up maybe start actually like working through it as if it were like an academic thing that I might actually be able to understand someday. So we'll see. I wasn't touching that. Okay. Hang on. Math new. Okay. I think we want to try math education. History and overview. Okay. Memories with Solomon Marcus. Was interested in the work of Solomon Marcus in mathematical linguistics as a high school student. Later, I had the opportunity to discuss with him about many topics. He was a polymath, wrote a paper together, refereed an editorial paper about his work in 2021. Samples of possible discussions are presented, some topology conjectures, self-dual theorem in geometry, results about Boolean algebras, B-ring and Euler formula. Young-Baxter maps, and discussion of sequences and series. Short appendix on poetry is also included. Could be interesting. Yeah, okay. That's not what I meant. Alright. And I lost it. There we go. Adolf Hurwitz and the Fundamental Theorem of Galois Theory. Königsberg Lectures of 1890 to 1891. In the winter semester of 1890-91, Adolf Hurwitz delivered a lecture course on Albertina University of Königsberg titled Der Algebraischen Gleichungen. These lectures contain a particularly clear presentation of the ideas of Évariste Galois, and in particular, a proof of the fundamental theorem of Galois theory formulated in the language of substitutions. The present paper analyzes Hurwitz's treatment of this result on the basis of lecture notes preserved in the ETH library in Zurich, together with material from his Mathematische Tagebuch 23 1920. Yeah. 23. After placing the Königsberg lectures in their historical context, we give an overview of their mathematical content and reconstruct in detail Hurwitz's argument leading to the fundamental theorem. So, give both of those a shot. See all recent. Oh, really? Fine. Well, if you insist on looking at recent. 3. Yeah, so I took kind of all of the papers that I was interested in and started working on, and I've just left them in the ribbon at the top because, you know, you can have as many tabs as you want. And it's not that bad, I promise. It's only that. But as I'm going through, I'm grabbing the individual papers, and my intent is to have those up until I put the video on YouTube. And once the video is on YouTube, then I'll kill the tab, just to make sure that I know what it was that I was talking about during any particular thing, and then I can add that to the information in the... I put a bibliography underneath all my videos as best I can, so that we know what we were talking about. Speaking of YouTube, yeah, one of my coworkers only had one window, and the tabs were so small you couldn't actually see what was inside of them. Like they were so small you didn't even, there wasn't an icon of like what site it's on or anything like that. She was just like, click, 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 click. I'm like, This was also the same lady who, when she minimized to desktop, just covered in icons everywhere. I'm like, please just add a folder and start dragging stuff in there, because this is insane. Don't do that. She could not find anything. And it wasn't even like, Newton, who like had a stack of papers this big and was like, oh yeah, I wrote a paper on that. Here. But the geometry. Like, unless you're trying to hide something from people, there's not much point in just making a complete and utter mess of your desktop. You can cluster thing. Well, that's the thing, is that she didn't. There was no such thing as any organizational pattern to her desktop. It was just a mess, and not even she could find things. I was just like, let me fix it. But no, I just kept my mouth shut. After writing Memories with Solomon Marcus 1 and 2, I felt we needed an unified version of them, with further developments included. Even from high school, I was interested in the work of Solomon Marcus C1 in mathematical linguistics. Okay, pause. Because it's in publishing house, it's not going to be available. Curses. Meetings with Solomon Marcus and... Oh, okay, yep. Interviews with Solomon Marcus. Curses. I'm one of the only people who actually eats these. Not olives. I mean, that's also a question, right? Is... Mm-mm. We may have to look at that one. On transcendental numbers, new results and a little history. Because I might be able to understand that. Anyway. I heard about the entropy of a translated poetry from an older colleague. My colleague and me won good prizes from these manuscripts. I published an exercise in the Romanian Gazette. Several years later, I wrote an article in the Romanian Mathematical Gazette on that exercise. Some math teachers from Bucharest wrote a book including results from that article. I had the opportunity to meet Solomon Marcus and discuss with him as a student and a researcher at the Institute of Mathematics of the Romanian Academy. As a result of our unexpected meetings, we wrote a paper together, C5. Got some ideas after a long discussion on Euclidean geometry. It might be the case that Solomon Marcus was actually impressed with the paper, 6. Also wrote on transcendental numbers, got that one. Several papers during those years. I'll refer to some remarks on 5 in the next section. He also invited my friends to many events. I spent many hours in the libraries studying his work in Boolean algebras, informatics, literature, and philosophy, trying to give a replica to his legacy. When I met one of the most important Romanian writers, Mircea Cartarescu, I asked him, "What do you think about the connection between mathematics and literature?" He only said to me, "Solomon Marcus." In 2021, I was an editor for an article about his work. In the present paper, we'll recall some previous results from 3 and 11, adding some interesting remarks and new theorems. As part of this paper can be considered a continuation of our axioms paper. Next 2 sections contain conjectures in topology and unification constructs in geometry. Section 5 is on Boolean algebra theory. We try to cast main properties of Euler formula in the Boolean algebra setting. Even in this rigid environment, we're able to obtain interesting results. We'll need to relax the restricting conditions imposed by Boolean algebras in order to obtain finer results. So we present the concept of weak B-rings, unifying structure for Boolean algebras and rings. Main B-rings for our theory will arise from Boolean algebras. Find an Euler formula for B-rings. There will be a section on arithmetic geometric series. Started as a high school problem, it led to a sophisticated approach to unify arithmetic and geometric series. An appendix on mathematics and poetry will also be included. After a series of conferences in intersection cohomology, I remembered some conjectures from the paper and improvised a beautiful problem which was well received. I will refer to enhanced versions of our conjectures below. Marcus and I formulated them after a long discussion on Euclidean geometry in late December, just before Christmas. For a Jordan curve in Euclidean plane, we consider the maximum diameter, big D, and smallest diameter, little d, passing through the corresponding center of mass. If L is the length of the given curve, then L over D is less than or equal to pi is less than or equal to big or L over little d. For any Jordan curve in Euclidean plane. Maximum diameter and smallest diameter passing through a corresponding center of mass. Right. So the inequalities can only become actually equal when big D or little d and or little d become constant, become equal to each other, making a curve. Wow, making a circle. Area of the domain inside the given curve is A, then little d times big D is going to be greater than A. which makes sense because if you're thinking about it, this is going to be essentially a rectangular bounded curve. So you're just fitting a rectangle around whatever curve you've drawn. The equation x squared minus L over 2x plus a equals 0 is not completely solved. If the given curve is an ellipse, solving this equation is unsolved. Last Congress of Romanian Mathematicians, attended by Solomon Marcus, was the 8th Iasi, Romania, 26th June to 1st July 2015. I remember happy discussions at this Congress. I addressed an interesting question to Alex Saussure, and it turned out that it could lead to a paper in collaboration with Barbu Berciano. In general, a theorem in Euclidean geometry is different from its dual. This happens because in the dual theorem we replace the points with lines, and lines become points. In this section we find a counterexample for the general rule. As Solomon Marcus was passionate about Euclidean geometry, the following theorem could have been included in our meeting discussions. Let us fix the terminology. A and B will be two triangles with vertices A1, A2, A3, B1, B2, B3, respectively. We will write that A A duals B, if and only if A1 is either, no. A1 is on B2, B3, and B1 is on A2, A3. Well, you know what I'm going to have to do here. Next question, is it even plugged in? On the back end. Let's see. Oh, cool. Good. All right. Still getting everything in order in here. It's fine. Okay. Scaladraw. Woo. Reset. Get this, flip to blue, minimal length, and then go. We say that we draw a triangle. Well, I should probably just do this one. I should, like, you know, make a good triangle, I guess. Okay, so go A1, A2, and A3. Then we said that A1 has to be on B2, B3, and B1 has to be on A2, A3. So this is A is dual with B. If anybody knows whether that is the correct words to use for that particular notation, let me know. Okay. So ugh. I don't think I want to do all those out. So theorem 4.1 says we're going to let O be dual with x, y, and z. Let x be dual with a prime. Let y be dual with b prime. Z be dual with c prime. Let a and b be dual with m. Let a prime and b prime be dual with m prime. A and C be dual with N, A prime, C prime be dual with N prime. B and C be dual with S prime, B prime, C prime be dual with S prime. Let M be dual with P and M prime be dual with P. N be dual with Q and prime be dual with Q. S be dual with R and S prime be dual with R. Then there will exist O prime, which has not been used so far, cool, such that PQR will be dual with O prime. The dual of a triangle will also be a triangle. Okay, I don't doubt that. But I do kind of hate all of this, like, faffing around here. Cool. toy model for Euler formula in Boolean algebras. Just gonna let the other one kind of go for a minute there. Wrong mouse. Toy model for Euler and Boolean algebra. Solomon Marcus was very keen on the Euler identity. We have many meetings in which we talked about it. I'm sure he would enjoy the following observations, which try to cast some properties of Euler formula in the Boolean algebra setting. Okay, with A defined with Boolean algebra A or and 0, 1, and exponent. We consider how a new Boolean algebra B, A cross A cross A, with pointwise operations. For x equals ABC belonging to B, we define three functions: exponential B, cosine B, sine B, which are mappings of B to B by the following formulas. E to the x equals exponential B on ABC, which is equal to A hat B hat 1, which belongs to B. Cosine of x equals cosine sub B of ABC, which is equal to 1 B hat C hat belonging to B. Sine of x equals sine sub B of ABC, which is 0, 0 C belonging to B. Following properties hold for the above functions. E raised to the x or y is equal to e to the x and x to the y. Which is still just our standard multiplication versus addition in their respective places. But the cosine function is not the same here. So this is cosine of x or y is equal to cosine of x and cosine of y. So in this particular case, this is not going to be the same as in standard Euler space. And sine of x or y is equal to sine of x and cosine of y, or cosine of x and sine of y, or sine of x and sine of y. So that's an interesting difference compared to Euclidean space. So with Euclidean space, when we had cosine of x plus y, we ended up with cosine of x times cosine of y minus sine of x times sine of y. Now the interesting question is here, why isn't that a part of this thing? And in fact, It is on the end of the sine function, or sine property in this particular case. Okay. Sine squared of x or cosine squared of x or cosine composed with sine of x is equal to sine of x and sine of x or cosine of x or and cosine of x, or cosine composed sine of x, which is equal to sine of x or cosine of x, or cosine of sine of x equals 0, 0, c, or 1 b hat c hat, or cosine of 0, 0, c equals 1. Goodness. Alternatively, following formula could be considered for the fundamental trigonometric formula for this setting. Sine of x or cosine composed with sine of x is equal to 1. I don't like that very much. Let j be 0, 1, 1 in B, then per Euler type formula, e to the j and x is equal to cosine of x or j and sine of x. As per usual, we're getting to the end of the hour, so everybody take a break, get up, walk around, stand up, stretch, do all that good stuff. I think we'll probably do a little bit of Tai Chi in this extremely tight space. Great. So see you in, roughly speaking, 3 minutes. And good luck out there, everybody. Woo. welcome back. Spouse moved a bunch of stuff that was downstairs that didn't need to be downstairs up into here. Quite frankly, it doesn't need to be in here either. But we'll deal with it. That is entirely the children's art supplies and things, I think. So that can go downstairs. Really should have looked at this earlier, I guess, but well, what can you do? Hey. Stuff fits. Definitely does not fit. Right. So, for anybody who's looking to do some interesting stuff, Tai Chi is really good for just like keeping active if you're a bit older. Or if you just want to like loosen your joints and stuff like that. This is not the Tai Chi in the park sort of stuff that you would do. Or stereotypically is like, you know, the older people's. Hey, Famished, how's it going? This is Tai Chi Chuan, which is typically like considered a combat martial art. So it is on the order of the same sorts of stuff as you would do with like karate or kung fu or anything else. So basically what we're doing is we're just spinning a little bit and then letting our arms flick upward. Usually get into it a little bit with like bending into the hips, and if you kind of lean into the inguinal crease, which is these two little creases just on either side of the groin, if you kind of bend and squash this area down, it allows you to generate a lot of power coming out of it. So typically we're just turning a little bit. Ow. Gotta watch out for the printer. So we just do a little bit of turning here to do this, and then when we get warmed up a bit, we usually go to up the front like this and bend the hips, or not even. At this point we're just bending the knees a little bit, cause the arms to kind of come up. Again, you're just kind of trying to use the swing energy that you would if you were like on a swing set. Right, bring yourself a little bit lower on the downswing and then push yourself up on the upswing, and it creates more energy. Hey Raven. I'm doing some Tai Chi. I didn't I didn't activate it. Psh. Ta-da, there we go. And typically we go for a couple of different things. So my instructor typically has us do stretches where basically we like bend backward, reach all the way up, and then come down and just relax a bit, and then lean back, come all the way up, come back down a bit, and do this a whole bunch until you're again feeling nice and loose. Then bend over and shake at the or rotate at the shoulder joint so that you're arms, when hung low, will just kind of move a bit. And then we put one foot in front of the other and do kind of the same thing, where here we're just going to use the swing energy to get our hands... Damn it, this place is so small. Right, so these are just warm-ups. These are not actually, doing Tai Chi. I'll show you the actual movements in a second, but these are good things that get your the fluids in the joints, called synovial fluid, and then also your blood just gets it all moving around. It's much healthier if you're doing exercise on a warmed up body. I think you all probably know that, but should be underscored practically every time you do it. So we round shoulders out a bit, and then coming forward we do what's called the bear. So we just kind of stand with your feet shoulder width apart, and then what we do is we lean into the inguinal crease into the left hip here with our arms out, and then we just shift the weight back onto our back foot. And then we turn this way, tuck into the inguinal crease here on the right side, and then shift over to the other. And basically this becomes kind of the natural motion that Tai Chi instructors want to encourage, I guess, reinforce over and over and over. You skip warm up. Do you get injured often? I will say that I am 43, so yeah. So after warming up doing bear, what we often do is we integrate arm movement with it. So in this case, this is what's called cloud hands. So we make this kind of circle up with the right hand. The left hand comes down to the side. And then from here, when we're tucked into this side, that's when we shift over to the right side, turn, swap, and then shift back to the other side. You do have some kind of hypermobility, yeah. So then we can turn this into a motion that goes back and forth like this. This is called cloud hands. The lead side is doing something akin to what's called a ward off. So you put your hand up like this and typically lean into it, and anybody else is going to be trying to meet this arm with their force. So typically you end up with arms against arms like this, and then if you have a proper structure and a proper root into the ground, so your feet are gripping the ground in a certain way, then you will actually be able to hold a particular position, not indefinitely, but certainly longer than the other person. If you're, extremely practiced, and especially if they're not. And you can essentially just out-exhaust the other person and start sapping their, not like energy, but you start sapping their muscular energy, their stamina, to be able to hold a particular position. Okay. So when we get into a stance with one leg forward, one leg back, typically there are 4 movements, which are considered the main positions on the it gets a little woo-woo, but at the same time, there's actual, like, thousands of years of practice of this stuff that's gone into it. So they know what they're talking about. It's just that the terms they use sound kind of magical, but they're not. So in studying the biomechanics of how Tai Chi actually works, we can start understanding, like, how some of the, like, magical terms came to be. So Qi, for example, is not some psychic energy that's like connecting you and the world and all this stuff. It's literally just like this biomechanical power that you store in your sort of in your hips, in the inguinal creases, in the groin area, and in your I forget the Chinese word for it. It's like Jichuan or something like that. I store a lot of stuff right here, but essentially what you do is you, like, move from your belly and try to get the biomechanical energy that you are storing in all of these muscles in here to then express themselves through your movements. And so it ends up doing some really big things for not a lot of energy cost. And again, typically, practitioners of not Tai Chi will end up, like, wondering, how is this even possible? Because, you're doing all these crazy things that basically all you're doing is using your momentum, your body mass, to be able to, like, push the force out of your body. I don't mean the force as in, like, chi, as in a mystical energy. I mean, like, you're able to essentially, if we do a push, for example, I'm not pushing with my hands. I'm going to, like, end up touching the person, moving my body forward, and loading all of that energy, then dig my back foot in, dig my back foot into the ground and press out of the ground. And when I press out of the ground, now I have the ability to move, usually you okay. So we're like, as I'm stepping forward, I'm here, kind of loading my arms up, then using my forward momentum to push, and then also when I've actually got them moving, then pushing with my arms against the ground. Typically the push is going to be because somebody is attacking you, or somebody is, like, in your space or whatever, and you want them out of your space. So what do? You push. And it is considered an attack, so you do have to, consider where you are in terms of self-defense. So typically the four main positions that are on our little chart correspond to the things that you do when your body is in control. So one of which is going to be the ward off, which is coming from usually the opposite side. And you come up with your hand, contact with your forearm, and typically you're using your back hand to just keep the muscles in proper, like, arrangement, and then straighten the body out. So from here to here, you're contacting and then getting into this, like, proper form where you're going to hold any amount of force. I'm digging into the ground and pushing both forward and backward with my feet, so that if somebody were trying to push me, it would be very hard for them to do that. The next move is called rollback. So basically, if somebody pushes here against my forearm and they try to push me, I'm going to essentially collapse this side and let all of their pushing force go that away. So we just go like this. Hopefully, that person, in attempting to push, is now going to overextend their body. Not hyperextend, that's different. Overextend their body and get off balance. So what do we do when somebody is off balance? Well, we can press. So this kind of goes against, like their pushing arms are coming this way. I'm now going to push against the ground and press my hand back into a ward-off position. So this is going to cause the person to essentially have to back off. And then there are the slightly aggressive ones. So, what is it? Ward off, roll back. Press, I guess, technically is like either you're returning to ward off or you are pressing into an attack position so that you can then lean back and go into a push. So typically the way we show this is we start with ward off, roll back, press, and push. And those are the four major movements that we do, which are typically the things you do when you are in control and remain in control. North, south, east, and west, the main compass directions. Then once we do that, then we have the four things that you do when you are out of control, or in order to regain control. So the first one is going to be pluck. So if somebody is coming at you and you can't just absorb their energy or redirect it, you have to force yourself to redirect it by doing a pluck. So essentially you grab their hand, you grab their shoulder, and you just go like this and force their energy to go off to the side of you. So pluck and then split, which is always a fun one. So we're coming up like this, and typically this is a slap right into the side of their face, including their ear, their eye, their nose, anything in there. Anything you could get a solid grip on, you just basically smack the hell out of them right in the side of the face. If they attempt to grab your hand, I don't remember what this one's actually called, but it's you basically are taking your gripping your own arm and then sliding it out so that they can't grab you anymore. And then exactly and then there's elbow. So I think that they're technically part of the same thing. So you've got your pluck, you've got your split, you've got, I think elbow is both movements. So there's a return, elbow, and then there's a return and shoulder. So you step forward and you're doing a shoulder strike into typically somebody's sternum. Maybe if you can, Dantien, that's the area down here. So you typically have all 8 of your major compass directions, which are like the main movements that we do in Tai Chi. So you've got your ward off, roll back, press, and push, followed by pluck, split, elbow, shoulder. And I was doing reps of that, just basically walking up and down the place that I had in the old place, which works fine enough. There's a few other combinations which end up using the same movements, but in sort of a different situation. We have a symmetric combo, which is called Dalu, where it's a periodic combo, so you do 4 movements. I think. Might be 6. Anyway, you're doing movements at the same time as your partner. However, you are phase shifted out from what they are doing. So it works. Basically, you start from a back-weighted position. You step up and do a palm strike, which is basically supposed to smack them in the face. They should block up and start doing a pluck. So you're trying to do a split, but this is like a straight split rather than a smack out from the side. Do a split like this. They do a pluck and grab my arm. While this is coming forward, I need to prevent them from getting an arm bar. So I step forward and block this like this, and then step sideways and try to elbow them. Or do an elbow on the first step and a shoulder on the second step. I think that's a better way to express it. Now, they are in sort of a defensive position, so they try and regain control by stepping forward and doing a split. So this person is right here. They try to do a split this way. I come up, step neutral stance, grab and do a pluck this way. They then try to use their elbow and shoulder to break my stuff. So after I do I do a pluck, but then I need to go further in order to make sure that their shoulder is going to miss my sternum. And then I step forward, do a split. They grab me into a pluck. I go forward and try to do a shoulder. And then I come back, block, and then work into a pluck. Try to split. Elbow, shoulder, block, pluck, split, elbow, shoulder, block, pluck. And then almost a half hour on this. Yeah. And then we've also been doing something I can't remember the name of. I'm thinking to myself, 再见, but that's see you later in Chinese. That doesn't really work. I'll remember it later. So there are 4 different combinations that you can do, and you are working, again, it's periodic phase shift from what your partner's doing. However, this one's more straightforward. I'm going to go forward on an attack, and then I need to go backward on a defense. So go forward on attack. I press into, or I push into the person's arm. They then redirect my force, and then I press using my back leg. I redirect the force back into their chest, and they then try and redirect my force again to get out of this area, because you don't want to collapse your frame. Right, so I am going this way. Then the person tries to push me here, so I use my ward off here and do a roll back this way, which is going to turn my body to this side. and then they're going to try and press, and so I put my hands into this position and do a second rollback, and now we're square with each other again. But here's the thing, I now have a bunch of loaded power into this hip. So from here, from this position, I can now go into a press. Nope, that's a push. I can go into a push, which then gets redirected, and then go into a press. And then again, they push me on this arm, so I do a roll back this way and a roll back this way. I transition to a push, get redirected, and into a press, and then roll back, roll back. So it's essentially like I'm trying to use the stored power, shift it up into the next position, and then my body ends up getting turned a bit, so now I've stored some power into the front hip, and I push that forward. It's essentially trying to move power from one foot to the other pretty seamlessly without ending up getting shoved off to the side, which my instructor does all the time. And I'm like, how can I prevent this? And we're just talking about it constantly. But, I mean, the fact is that he's 15 years older than me and has gone on to practice all of this stuff to become a master in Malaysia. So, like, I'm not going. From here, there's also a few things. He was saying, like, when you do the push, you can advance, and when they do the push, you can also retreat. So you can get some footwork going in there. You can also decide at some point that when the person comes and pushes in, instead of going to a rollback this way, you could actually swap and do a rollback this way. Which is great, but now, like, all of the forces have now changed direction, and which also means that your like your weak line here, if somebody were to just push me this way, like I'm gonna have to step if I lose my balance. Your weak line stays the same, but now the force that you're going to have, like, this is strong, this is strong. I'm pushing up and pushing out this way. I'm now weak on this side. So if they just, like, get on this side of me and push this way, like, that's the weak side. I can fall over. And then, for extra challenge, you swap legs. And actually, I lied, because while we're both on the same foot, I'm going to push this way, so I'm going to push to my left, or press to my left. And then when we come back, this person is going to press to their right. So we're actually mirrored in hand movement. Our hand movements are mirrored from each other, and so it's really weird. Hey, Zach. How's it going? Happy Monday to you as well. We were just discussing some Tai Chi stuff. I spent far too long on it, but nonetheless. Trying to get in some reps while we're in this teeny tiny space is somewhat important. Got to do some exercise. It might be more important if you're in a smaller space. Let's see. We were talking about Flor and Felix Nikita's Memories with Solomon Marcus 3. They had done some work with Solomon Marcus on B rings and trying to like define particular metric spaces, and it may not be metric spaces. Yeah, doing duals within Euclidean geometry and trying to show that, like, you know, if you have specific duals, dual relationships, that other dual relationships will show themselves. This one was working on trying to figure out the Euler formula in a Boolean algebra setting. Make sure you have a second for your duals. Oh boy. Current Euler formula leads to the existence of a certain co-ideal. Hopf algebras theory, all sorts of other stuff like that. Oh, yeah. Oh, man. It's been a long day. My kid's been home. Yep. I assume that's what they mean. But yeah, structures which unify Boolean algebras and rings. So yeah, probably. You won't be happy with me, Zach. There's a lot of stuff I just don't recognize. There's multiple places where it was discussing. I think it was the last paper was discussing compact metric spaces. I was like, I mean, I studied that. I studied, I believe, all of those individual definitions of like compact and metric spaces, and we had talked about them in real analysis, I think. And if not, we talked about like most of the separate parts. I was just like, yep, don't remember much about that. It's been 2 years, of course, but still. Alright, so many mathematicians think that the rings and the Boolean algebras are very different structures. However, the study of their axioms led to B rings. We'll give the definition of weak B ring below. Weak B ring is a 6-tuple. So this is our set using the technically or Boolean operator 0 dot, which seems to be multiplication but not and, 1 and exponentiation question mark. Oh, it literally explains it. I need to read ahead of what I'm... Anyway. X is a set. Or and dot are binary operations on X, and 0, 1 belonging to X. And, yep, that is a unary operation on X. X hat, it belongs to X. These obey the following axioms. Not quite exponentiation, but... Oh, yeah, no. It is not exponentiation. Alright, X or 0 is a commutative monoid. So, or operation has associativity. Or operation is commutative. Or operation has 0 identity. X dot 1 is a monoid. So here we have dot associativity. Here we have dot identity, left or right. 0 is an absorbing element, so x dot 0, 0 dot x is going to be 0. So it's effectively multiplication. Second operation is distributive with regard to the first, so x dot parentheses y or z is x dot y or x dot z. And x or y dot z is going to be x dot z or y dot z. Unary operation has some basic properties where we have x hat hat is x, so it goes back around to itself. X or x hat is the same as x hat or x, so the hat unary operation is commutative on either property, so dot or. Let A space A be A or and 0, 1 hat be a Boolean algebra. We'll consider the following operations on A cross A, or A by A, I guess. AB or CD is going to be equal to A or C, B or D. And AB hat is going to be the same as A hat, B hat. And AB and CD is equal to A and C, A and D, or B and C, or B and D. Notice that AB and 1, 0 is equal to AB. And 0, 1 and 0, 1 is equal to 0, 1. We'll use the following conventions and notations. Operation AND has priority over operation OR. We'll omit the simple AND when there's no danger of confusion. Let H be 0, 1. Gee. It looks exactly like multiplication. Except the weird behavior in that other one. Let H be 0, 1, then AB is equal to A0 or B0 is equal to A0 or bracket 0, 1 and B0, which is equal to A or HB. Or I guess A or H and B. With the above, A by A is equal to A by A or and 0, 0, 1, 0 hat is a weak B ring. And then proof that that is a true statement. It's a very short proof. One could meticulously check all axioms of a weak B ring. Main parts are to verify associativity of and distributivity of and with regard to or. Alternatively, one could observe the analogy with the ring complex or C space of x over x squared minus x is equal to C space of h with h squared equals h. Euler formula for weak B rings. For a Boolean algebra A or and 0, 1, hat. Let 0 not be e belonging to A. We define the exponential function e to the blank as a map onto A by rule e to the x is equal to x hat or e. Also, we consider the trigonometric functions c sub b, s sub b, a mapped to a, defined by the rules c sub b of x equals x hat, and s sub b of x equals x. It's easy to check that. So say you e to the x or y is equal to e to the x and e to the y. C sub b of x or y is equal to c sub b of x and c sub b of y. This is the same as what we were seeing up above with the actual literal cosine sub b, or sine sub b. It's just now they've shortened it to just S and C. Right, and S sub b of x or y is going to be equal to, so this is again very similar to the actual sum and difference formula of actual trigonometric functions in Euler space, or not Euler, Euclidean space. But the problem here is that this extra term is not here at the end of this statement. It is now added on to the end of what would have been the standard sine formula. And again, it makes sense when you break down all of the actual operations that work here, but it's just different and weird. And then these floating ands bother me, but sure, why not? It's the same as squared effectively. The sum of sine and cosine is going to be equal to 1. We don't even need the squaring necessarily. Exponential map can be extended on A by A as follows. E of AB is equal to e to the A and B hat. E to the A and B equals A hat or E and B hat. A hat or E and B. So E of A or HB is equal to e to the A or HB equals e to the A times B hat or h times e to the A B, which is the same as e to the A times B hat or h times e to the A times B. with the above notations. Euler type formula holds. E of hy is equal to e to the hy is equal to c sub b of y, or h times s sub b of y. Also, in particular, e to the h equals h. The map phi a cross a to a cross a, defined by the rule xy map to e to the hy, or c sub b of y, s sub b of y, is a solution for braid condition that is very similar to, well, not quite. Because it's not y. That's the input for our cosine and sine functions. Solution for braid condition phi 1, 2, phi 2, 3, phi 1, 2 is equal to phi 2, 3 times phi 1, 2 times phi 2, 3. The compassion of the above terms completes the proof. Applying the Euler formula for Boolean maps leads to the following theorem. For x belonging to A, the map phi a cross a to a cross a, defined by the rule a to ab map to a or xb, x hat or xa times b, is a solution for braid condition phi 1, 2, phi 2, 3, phi 1, 2 is equal to phi 2, 3, phi 1, 2, phi 2, 3. Complications, or the computations, are quite involved. Right. Okay, let's look at this one. Series and sequences. Section is based on discussions at Math Cafe 2026. Started as a high school problem that led to a sophisticated approach to unify arithmetic and geometric series. The idea is to embed the sum of non-zero digits and a corresponding geometric series into a unique formula. For example, the following matrices are an illustration for this unification theorem. A is going to be equal to 1101, and B is going to be equal to 2001 half. Let A belong to M2 in R, such that the determinant of A is 1. That's fair as it is. We're good. Then the sum as k goes from 1 to 9 of A to the k is equal to the trace of A plus 1 times the trace of A cubed plus 1 times A to the 5th. References. What the... Provided without detail for the reader. Oi. March is a month which should be dedicated to Solomon Marcus. wrote an article in a prestigious literature journal about the meetings of Solomon Marcus with Nikita Stănescu. Below we give a translation of the poetry from that article. As a noble replica to Poetica Mathematica, the poet wrote on appendix the Poetic Mathematics. Present a translation of well-known Romanian spring song. In this case, we are interested in saving rhyme and rhythm of the Romanian song rather than making a very rigorous translation. Happy, happy celebration, spring is coming from vacation. Let's go out with the other kids, let's pick flowers from the fields. So close. But alright, well, that's kind of interesting. Adolf Hurwitz and the fundamental theorem of Galois theory, the Königsberg lectures of 1890 to 1891. Maatdeke, Hoensbroek, Netherlands. Printed today. I read that before, so we're going to skip that. Seems reasonable to assume that someone who teaches Galois theory has studied Évariste Galois' Mémoire sur la condition de résolubilité des équations par radicaux, or at least has attempted to do so. Anyone presenting a theory generally benefits from being aware of its original formulation and argumentation. One would argue that should be the case. It is not always the case. So, generally speaking. It is well known that the memoir is difficult to access. In what follows, I will show that Adolf Hurwitz, 1859 to 1919, can help to make it more accessible. Recently, a series of lecture notes by the student Emil Leutnerger, 1894 to 1978, became available. Between 1915 and 1917, he attended lectures in Zurich given by Adolf Hurwitz. These are extensive notes from the courses Algebraischen Gleichungen, Zahlentheorie, and Funktionentheorie. Substantial material is known for the courses Zahlentheorie and Funktionentheorie. Numerous notes by Hurwitz himself exist, and both courses have been published in book form, first by Nikolaus Kritikos, second by Richard Kural. In this article, we focus on the course Algebraischen Gleichungen, thanks to the efforts of Mrs. Evelyn Bush, ETH Library, University Archives of ETH Zurich. The surviving manuscripts of Hurwitz for this course have been digitized and made accessible as PDFs. Among this material, there is a lecture course from winter semester in Königsberg. The course Theorie der algebraischen Gleichungen in Königsberg contain the following chapters: the algebraic solution of equations of the second, third, and fourth degree, the theory of symmetric functions, basic concepts of substitution theory, the insolvability of equations of the fifth degree, Galois theory, application of Galois theory to the algebraic solution of equations. In the lectures in Zurich, the section on Galois theory is absent, except for the course of 1909. Around that time, a note also appears in Mathematisches Tagebuch, I forget what the German word is for number in that case. 23, in which he sets out the main theorem of Galois theory. A marginal note referring to this also recorded in the manuscript of Königsberg lectures. It appears that in 1909 he consulted Königsberg lecture notes. We focus on that section of his Mathematisches Tagebuch. Photograph of this section is included. Lecture notes of Königsberg and Zurich occupy a special place in the teaching of Galois theory, particularly because they were delivered by Adolf Hurwitz. He still treats the material entirely within the classical 19th century tradition of substitutions. In this way, he connects directly to the original Mémoire of Évariste Galois, whose central ideas he carefully follows and explicates. In doing so, he assumes that Galois, without explicitly reformulating it, already possessed a notion of what he called Rationalitätsbereich, and by Dedekind, a field, Körper. He consistently refers his students to contemporary literature, including in this case a German translation of Galois' Mémoire, and to the book by Eugen Netto, Substitutionentheorie und ihre Anwendungen auf Algebra. The notes in this course are preserved in the ETH Library at Zurich. For the work of Galois, Hurwitz refers to Abhandlungen über die algebraische Auflösung der Gleichungen by Abel and Galois, which were republished in German translation in 1889 by Maza. All right, 3 minutes. Be right back. Thanks everybody for coming. We'll finish this up and then probably raid out because it's right about 1 o'clock. So see you in a minute, or 3. All right. Dost thou in hoist? We typically do arm curls on these 20-pound weights, and then do a couple more little exercises just to keep the arms in shape, because I do a lot with legs. Always have. Right, and then up. All right, don't drop it. I grab one, up over the head. Get the triceps. Okay. Ugh. Good times. Hopefully didn't wake my son up. Not like I was doing much, but I'm talking and the door was open. Okay, so let's try and see where we're at here. In the present article, we work out a proof of the main theorem of Galois theory, as Hurwitz recorded it in his diary. Although the proof is rather subtle, it is at the same time of great beauty. We provide the theorem in a concrete situation so that the complexity is somewhat reduced, while the essence of the proof is nevertheless preserved. From the passage in Hurwitz's diary, dated 1st July 1909, in which he proves the main theorem, reproduced below, we first sketch the context in which the discussion is placed. For convenience, we take the base field to be rationals. Let f of x be a rational function, be a polynomial, 4 distinct roots, and let L be rational of x1, x2, x3, x4 be the splitting field of f. According to lemma 2 in Memoir of Galois, there exist natural numbers n1, n2, n3, n4 such that the 24 values n1 x sub s1 plus n sub 2 n sub 2 times x sub s2 plus n sub 3 times x sub s3 plus n sub 4 times x sub s4 are pairwise distinct, where s permutes the numbers 1, 2, 3, 4, starting from v1 equals n1x1 plus n2x2 plus n3x3 plus n4x4. All these values belong to L. We denote them by v1, v2, v3, etc. through v24. 4 factorial, yeah. Given a value v sub I, one may associate it with a substitution from S4. For example, n1x3 plus n2x1 plus n3x4 plus n4x2 corresponds with substitution x1, x2, x3, x4, x3, x1, x4, x2. So they're not even rotated in order, they're randomized as necessary. We now assume the field R contained in L. The fact that F is belonging to R of X will be important later in connection with the application of lemma 1 to Galois. Aim is the following. Elements V1 through V24 are numbers in L. We wish to determine functions R1, R2, R3, R4 in rational space, which yield the values x1 through x4 respectively, such that for every I from 1 to 24, V sub I is equal to N1 R1 VI plus N2 R2 VI plus N3 R3 VI plus N4 R4 VI. Is that R1 of VI? I think it must be. Yeah, because R is rational functions. Yeah. Functions. Jeez. Right. N1 R1 of V sub I plus N2 R2 of V sub I plus N3 R3 of V sub I plus N4 R4 of V sub I. Purpose is therefore to reconstruct numerical value V sub I in the original linear combination, and thereby also the corresponding substitution S sub I is R1 V sub 1, R2 V sub 1, R3 V sub 1, R4 of V sub 1, compared to R1 of V sub I, R2 of V sub I, R3 of V sub I, R4 of V sub I. This line of reasoning appears in lemma 2 and 3 and proposition 1 of Mémoire. Below follows an adapted transcription of the relevant part of Hurwitz notebook in German. Yep, cool. Yep. Okay. Define f of v to be equal to the product of v minus parentheses u1 x sub alpha plus u2 x sub beta plus u3 x sub gamma plus u4 x sub delta is equal to the product, as I goes from 1 to 24, of v minus v sub I. And where r equals 24, this must be equal to v to the r plus a1 v to the r minus 1 plus a2 v to the r minus 2, etc., all the way down through a sub r. 25 terms. Awesome. Coefficients a1 through a sub r are rational functions in the variables u1 through u4. Moreover, a sub I is homogeneous to the degree of I. We assume that the elementary symmetric functions x1 through x4 belong to the field R. By a rational function, we always mean a function whose coefficients lie in R, the field. Elements x1 through x4 are mutually distinct. Let v sub I equal u1 x of alpha plus u2 x of beta, etc. Differentiating this identity, the identity f of v sub I equivalent to 0 with respect to u1 yields the following. F prime of f prime of v sub I times x sub alpha plus partial derivative of a1 with respect to u1 of v sub I raised to the r minus 1 plus, etc., all the way out to partial derivative with respect to a sub r, no, partial derivative of a sub r with respect to u1 is all equal to 0. From this, one obtains analogously x sub alpha is equal to r1 v sub I, x sub beta is r2 v sub I, etc. through x sub delta is r4 of x v sub I. Really hope I didn't say multiply again. I'm losing track. It is, generally speaking, quite late. The scheme given here contains all r equals 24 permutations of the 4 elements, x1 through x4. The denominator is f prime of v sub I is equal to the product of v sub I minus v sub k as long as k is not equal to I and are not identically 0 themselves. One can choose integers a1 through an such that v prime of v sub I is not equal to 0. In that case, r sub k of v sub I are rational functions of v sub I. Let g of v be the irreducible factor of f of v, which is equal to the product of v minus parentheses a1 x sub alpha plus a2 x sub beta, etc., which vanishes for v equals v1, which is equal to a1 x1 plus a2 x2, and whose zeros, after possible renumbering, are v1 through vm. Then the m substitution. S sub I is equal to R1 of V1 through R4 of V1, substituted for R1 of VI through R4 of VI. Define a system G with the following properties. Every rational function f of x1, x2, x3, x4, whose value phi of x1, x2, x3, x4 emits the substitutions of G and has value belonging to the field R. Every rational function f of x1, x2, x3, x4, whose value phi of x1, x2, x3, x4 belongs to the field R, emits the substitutions of G. G is a group. A substitution S belongs to G if and only if every rational function phi of x1, x2, x3, x4 belonging to field R emits the substitution S. Hurwitz proves these statements using an auxiliary lemma and shows that this correspondence between rationality domains and substitution groups yields precisely the fundamental theorem of Galois theory. Okay. Suppose that the function phi of x1 through xn is invariant under substitutions of G, then phi of x1 through xn is equal to 1 over m times big phi of v1 plus big phi of v2, etc., through big phi of vm is rational. Okay. During the lecture in 1909, Hurwitz addressed his students as follows. Galois ist einer der größten mathematischen Genies aller Zeiten. Yup. Geboren 1811, gestorben infolge eines Duels 1832, ist nur 20 halbe Jahre alt geworden. Schön mit 19 Jahren war in Besitz der nach ihm benannten Theorie, welche die Lehre von den algebraischen Gleichungen ein ganz neues Gepräge verlieh. Oi. Guten Tag. How's it going, Phobos? Wie geht es Ihnen? Wie gehen Sie? Ja. Ja, gut. Oi. Two lecture courses by Hurwitz devoted to Galois theory are known. First was given in Königsberg during the winter semester of 1890 to 1890. Whoa, not that much. I gotta go take this over to... Galois is one of the greatest mathematical geniuses of all time. Born in 1811, died as a result of a duel in 1832. He was only 20 and a half years old. At the age of 19, he was already in possession of the theory, which is similar to the doctrine of the algebraic, a whole new character. Ew. I don't know what happened there. Algebraic equations of an entirely new character. There we go. That's better. Thank you. Okay. During the winter semester of 1890 to 91, when Hurwitz was about 31 years old. The second was delivered in Zurich, the semester of 1909, when he was about 50. Königsberg course is the more extensive one and follows quite closely Galois' difficult Mémoire. In 1909, Hurwitz returned the Königsberg material in the present article with only minor adaptations. Königsberg lectures are of particular interest not only because they offer insight into Hurwitz as a teacher, indeed an excellent one, but also because they provide a valuable point of access to Galois' Mémoire. In this way, Königsberg lectures form an illuminating bridge between Galois' original ideas and their later exposition to Hurwitz's teaching. Alright, so that's the one from Galois. I think we'll save this one for next time. This is the On Transcendental Numbers, New Results and a Little History. Published, well, 2013 anyway. To took a bunch of... Yeah. Took a bunch of information out of here, so... Or never had it in the first place. Either way, it's all good. Alright, we are going to open that door because it is getting hot in here. And shut off the lights for that matter. Okay, now you're just lying. I hit raid and it was like, oh, this person's been live for 73 hours. This person's been live for 72 hours. Like, no. Let's go see Rogan, because I haven't seen Rogan in a while. I believe he may end up leaving to send everybody over to a different location, but nonetheless. Rogan 27 is a friend from Virginia Tech and the Geek and Sundry days. Fan of yep. Damn it. Eric Campbell. Who's one of the GMs over on currently Alt Haven, formerly they had a different name. Yeah, doesn't matter. Anyway, I will see you all tomorrow. We'll be probably playing Blueprints and trying to figure out some more stuff with the crazy puzzles that we've found and have dug up thus far. And then we'll be back on Wednesday for more yeah. Damn it. Wednesday is our calculation day for math. Then Thursday is going to be TTRPG prep, because I've got a lot of stuff to prep still. And then Friday we'll do some more game stuff. So see you all later. As long as everybody's healthy in my house, we're going to be all right. So